now I want to move on to mathematical induction using factorials. Now we'll just have a little bit of revision of what factorials are. So first of all, let's remember what the sign for factorial is, and that's this exclamation mark here. So we have n exclamation mark, and this is our factorial sign. And now what does n factorial actually mean? Well, what that means is starting from the number n, we have that number multiplied by one number smaller than that, and then another number smaller than that, so on until we have times 1. So an example of that is if we have 5 factorial, we'd start off with 5 and then one number less than that, which is 4. And then 3 times 2 times 1. So remember, you just multiply by the next number down until you get to times 1. So it always finishes with multiplied by 1. This over here is very important for what we use in the induction process. So we have that n factorial equals to n times n minus 1 factorial. Well, what does that mean? Well, that means that if we have 5 factorial, that's actually the same as saying 5 times 4 factorial. And that makes sense because 4 factorial is 4 times 3 times 2 times 1. So if I add a 5 in front of that, that becomes 5 times 4 times 3 times 2 times 1, doesn't it? And that's why it becomes 5 factorial. If you ever see a factorial, so like 4 factorial here, or n minus 1 factorial over here, and you see that the number is multiplied by 1 more than what it is, then you can assume that it's going to be that one number more than that factorial. So to make myself more clear, what I mean is if you see n minus 1 factorial and it's being multiplied by a number greater than that, you can say it's going to be that number factorial. An expansion upon that is, for example, if we have n minus 2 factorial and then we have multiplied by the number greater than that and then the next number greater than that, you can still assume that's going to be n factorial. So for example, you have 3 factorial, which is 3 times 2 times 1, times by 4, and then 5, you can assume it's 5 factorial. Now this over here is the one we're going to use most frequently for our induction with factorials. So I want you to remember that if you see something that's factorial, but there is being multiplied by one number greater than it, you can assume it's a one number greater than factorial. All right, I think the best way to show this is by using a question. With question 4, we want to prove that 2 times 1 factorial plus 5 times 2 factorial, so on, until the general equation of n squared plus 1, n factorial, equals to the right-hand side that we have here. So remember, the first thing we do with step 1 is we want to work out what the first value of n is. And you can see quite obviously it's going to be 1 because that has to be 1 factorial, and 1 squared plus 1 gives us 2. So we want to show in step 1 that it is true for n equals to 1. So we write this, the left-hand side, which is using the general formula, and we substitute in 1. So we have 1 squared plus 1 times 1 factorial, just 2 times 1 equals to 2. Now using the right-hand side, we have 1 times 2 factorial, so that's 1 times 2, which equals to 2 as well. So since the left-hand side equals to the right-hand side, we can say therefore it is true for n equals to 1. So I want you to write all these steps when you're actually setting it out in the exam. And now moving on to step 2, we assume that it is true for n equals to k. That is, we write the new equation using k. So we're assuming when we substitute in k, the left-hand side here does indeed equal to right-hand side. And we're using this assumption for the next step. So now we can move on to step 3. We want to show that this is true for n equals to k plus 1. This left-hand side of the equation equals to the right-hand side. So we want to prove that. Now, how do we get this equation here from that? Well, we're substituting in k plus 1 to wherever there's n essentially. Now for the left-hand side, what we always do is we add in an extra value at the end. So this is the extra value we're adding in. And how we do that is, instead of n squared, I'm writing in k plus 1 squared. So I have k plus 1 squared over here, and that's what gives me k squared plus 2k plus 1. And because I'm adding 1 to that, that's how I get k squared plus 2k plus 2. And this just comes from the n factorial there. So I get k plus 1 factorial. Whereas over here, instead of the n, I write k plus 1. Instead of n plus 1, I'm writing k plus 1 plus another 1, which is how I get k plus 2 factorial. So now we've gotten this equation, and I want to prove left-hand side equals to right-hand side. With proofs, we always start with one side. So let's start off with the left-hand side. And remember, this is when we need to apply the assumption from step 2. So I want you to identify which part of this looks like the left-hand side of our assumption in step 2. Yeah, that's right. It's going to be this part here, isn't it? Up until k squared plus 1k factorial, this looks exactly like the left-hand side of step 2, which means that I can just substitute in k plus 1 factorial instead of that. So instead of writing all of that, I'm now just writing k times k plus 1 factorial. And this just stays the same. And now remember what I taught you before, which is always try and keep in mind what the right-hand side looks like, because that is essentially what we're trying to do. So let's go back and have a look at the right-hand side. So we want it to look like k plus 1 and then k plus 2 factorial. So having a look here, we can see we have k plus 1 and k plus 1 there. So we know that we need that factorized out. So I factorize out k plus 1 factorial, and that's going to leave me with k plus k squared plus 2k plus 2, and that just becomes k squared plus 3k plus 2, and now I factorize that, and this factorizes to k plus 1, k plus 2, k plus 1 factorial. Now, looking back on the right-hand side, you can see that we have the k plus 1, but what we don't have is a k plus 2 factorial. So somehow we have to think of a way to make this section equal to k plus 2 factorial. Now, can you think of a way that we can do that? Well, looking back on what we learned about factorials, or what we revised about factorials at the start of this, we learned that if you have a number factorial and it's multiplied by a number that's 1 greater than that, then you can make it become the greater number factorial. Let's say, for example, that k equals to 1 and this equals to 2 factorial, and this is 3, then 3 times 2 factorial is the same as 3 factorial. So that means I can actually make this equal to k plus 2 factorial, because k plus 2 is 1 more than k plus 1. And that's how I make it into this part into k plus 2 factorial, which you can see looks exactly the same as the right-hand side. So we can say equals to the right-hand side. So since we've proven the left-hand side equals to the right-hand side, we can say, therefore, it is true for n equals to k plus 1. Okay, so remember, we have to write this. And now we have to write the conclusion, which is, therefore, the statement is true for all integers of n is greater or equal to 1. Now, for this question, the hardest part is moving from this to here. So the most difficult part for all your induction questions using factorials is recognizing that if it's multiplied by one number greater, it becomes that greater number factorial. And then you make it equal to the right-hand side.